Hello, my name is Jacob Rogers, and this is a presentation on the hypervelocity impact response of polyethylene plates. Listed on this slide are the authors. The first row denotes the research advisors, and the second row denotes the students in contributing order. The authors and I currently research in the J. Mike Walker 66 Department of Mechanical Engineering at Texas A&M University. This is an overview of the presentation, including motivation, methodology, and analyses of our work. Understanding how polymeric materials respond to hypervelocity impacts macroscopically forms a baseline for comparing how polymer microstructures and chemistries affect hypervelocity impact responses. This understanding is vital because it enables the ability to tune material structures for anticipated hypervelocity threats. For more information concerning the motivation, please see the companion paper. Both ultra-high molecular weight polyethylene and high-density polyethylene are thermoplastic, semi-crystalline polymers possessing viscoelastic behavior that is highly dependent on temperature, strain, and strain rate. The polymers differ in molecular weight and crystallinity, with high-density polyethylene having a higher crystallinity, while ultra-high molecular weight polyethylene possesses a much higher molecular weight. At lower velocities, ultra-high molecular weight polyethylene demonstrated higher perforation energy than high-density polyethylene. It has also been shown in the literature that the materials have different damage morphologies at low impact velocities. Studies have also shown that ultra-high molecular weight polyethylene exhibited better hypervelocity impact performance than Kevlar, which is used in conventional Whipple shields. Achieving hypervelocities, which we will denote here as velocities greater than 2 km per second, is difficult in general, especially as the projectile size and mass increase. The experiments in this work were conducted using a two-stage light gas gun shown on this slide, which is located at the Hypervelocity Impact Laboratory at Texas A&M University. The two-stage light gas gun was built by Physics Applications Incorporated and is capable of accelerating 2 to 10 mm diameter projectiles to velocities of 2 to 8 km per second. The lab is part of the Materials for Extreme Environments research group that encompasses other experimental expertise and novel modeling efforts. Apart from the work discussed in this presentation, our group also studies impacts to various concretes, polymers, composites, and water droplets at various impact configurations, as well as shock fronts. Two-stage light gas guns accelerate projectiles by compressing a light gas, typically hydrogen or helium, to high pressures using a consumable polymer piston and a gunpowder charge. The gases released from the powder charge combustion propels the polymer piston down the pump tube, compressing the light gas. Once the light gas reaches a critical pressure, a diaphragm ruptures, releasing the high-pressure gas that accelerates the projectile. The projectile is protected during acceleration by a 4-piece polymer sabot. The sabot is aerodynamically separated from the projectile during free flight. Before entering the target tank, the projectile passes through 2 lasers. The measured time between the laser interruptions, coupled with the fixed distance between the lasers, provide an accurate projectile velocity. Regardless of the velocity, a dynamic delay generator accurately generates a delay trigger for the high-speed camera. Finally, the projectile enters the target tank. The Shimadzu HPV X2 high-speed camera served as the main diagnostic instrument for these experiments. The camera is fixed perpendicular to the axis of penetration, which is defined by the trajectory of the projectile. High-power LED lights face the camera on the other side of the target tank and serve as the primary illumination for the impact event, resulting in shadowgraphic images. A dynamic delay generator triggers the camera, which captures the impact event, including projectile flight, projectile impact, and debris cloud expansion. The front face debris cloud ejects from the impact face, expanding in the uprange direction. The back face debris cloud ejects from the rear face, expanding in the downrange direction. Qualitative analyses of the impact event images were used to determine the material response, for example, target fragmentation versus target melt. Motion tracking software was used to determine the velocity of the leading edge of the back face debris cloud as a means to quantify the hypervelocity impact performance for the 2 candidate materials. The target specimens are sandwiched between 2 A36 steel plates, each having a cutout in the center, effectively inducing axisymmetric boundary conditions on the polymer specimens. The target assembly is fixed rigidly in a target fixture, such that the axis of penetration is aligned with the center of the target specimen. A total of 27 hypervelocity impact experiments were conducted and analyzed. For these tests, 10 mm 1050 aluminum spherical projectiles were accelerated to velocities ranging 2 to 7 km per second. The impacted specimens were 30.5 by 30.5 centimeter square plates, all with nominal thicknesses of 6.35 mm. These videos display high-speed images at 1 million frames per second of hypervelocity impact events for various velocities across the tested regime. The tests shown on the top are of ultra-high molecular weight polyethylene, and the tests shown on the bottom are of high-density polyethylene. The impact velocity corresponding to each video increases from left to right and is provided at the top of the figure. Ultra-high molecular weight polyethylene fragments into finite particles, while high-density polyethylene displays apparent bulk melting and condensation during debris cloud expansion for the same impact velocity and projectile. A single frame is taken from each of the previous videos at 39 microseconds for comparison. The series of images indicate that the debris clouds of ultra-high molecular weight polyethylene tend to be composed of fragments, and the average size of these fragments in both the front face and back face debris clouds decrease with increasing impact velocity. In addition to fragmentation, a small region of the front face debris cloud near the impact surface shows signs of minor melting. In contrast, high-density polyethylene exhibits little to no fragmentation. Instead, the front face and back face debris clouds for high-density polyethylene exhibit apparent bulk melting over the velocity regime tested. For both materials, the average front face and back face debris cloud sizes increase with velocity. It is also evident from these images that at a given impact velocity, the back face debris cloud of ultra-high molecular weight polyethylene and high-density polyethylene tend to be the same shape and size, while those of the front face debris clouds differ significantly. The leading edge velocity of the back face debris cloud was measured and averaged over its entire expansion. Here, the back face debris cloud velocity is plotted as a function of impact velocity. Due to the finite pixel size in the high-speed images and the short time scales of the hypervelocity impact events, systematic tracking errors were introduced into the measurements and are displayed via the error bars on the plot. Interestingly, although the hypervelocity impact response of the two materials differ qualitatively, the polyethylenes have nearly the same backface debris cloud velocities for the velocity regime tested. If the change in velocity between the incoming projectile and the backface debris cloud serves as a metric for energy dissipation, both polyethylenes dissipate the maximum amount of energy at an impact velocity of approximately 6 km per second. Post-impact forensics were performed on all the specimens to characterize the hypervelocity damage response. Mass loss measurements are plotted as a function of impact velocity on the right. The mass loss plots show that for a given impact velocity, ultra-high molecular weight polyethylene loses more mass than high-density polyethylene. The difference between the mass losses in the polyethylenes is likely a result of their distinct apparent failure modes. For example, the brittle behavior versus the ductile behavior. Ultra-high molecular weight polyethylene is more prone to fragmentation and fracture. When subjected to impact loadings consistent with those of hypervelocity impact, ultra-high molecular weight polyethylene's long polymer chains and higher degree of chain entanglement prohibit relative polymer chain motion that could occur at lower strain rates. As a result, the polymer chains break, and this breaking is exhibited macroscopically as fragmentation and fracture. In contrast, the shorter chain lengths and lower degree of chain entanglement in high-density polyethylene are more conducive to relative polymer chain motion, allowing for more larger-scale deformation, which results in less mass loss. Additionally, the hypervelocity impact-induced perforation region was analyzed for all specimens. The measured perforation radius is shown as a function of impact velocity for both ultra-high molecular weight polyethylene and high-density polyethylene. While ultra-high molecular weight polyethylene loses more mass at similar impact velocities, high-density polyethylene exhibits a larger perforation diameter for the impact velocity regime tested. This increase in hole diameter is likely due to the apparent melting behavior resulting from adiabatic heating and thermal softening in HDPE. High-density polyethylene specimens seem to melt even after the projectile has completely perforated, resulting in residual plastic hole enlargement. This feature is not evident in ultra-high molecular weight polyethylene. This notion further validates the claim that the higher mass loss seen from ultra-high molecular weight polyethylene experiments is attributed to its brittle-like response, while high-density polyethylene conserves more of its mass through large-scale deformation. The series of images on the right show the macroscopic characteristics of the damage regions for both materials. The images clearly show that, for both materials, the perforation radius increases with impacting velocity. Also, the perforation radii are larger in high-density polyethylene than ultra-high molecular weight polyethylene for the entire velocity regime tested. The images indicate that ultra-high molecular weight polyethylene failure is both brittle and plastic in nature. This results in multiple fracture planes initiating, while the plastic behavior and viscous effects prevent the development of dominant fractures. Significant residual out-of-plane plastic deformation was observed in both ultra-high molecular weight polyethylene and high-density polyethylene specimens, but more so in high-density polyethylene. The lack of a dominant fracture plane is even more prevalent in the high-density polyethylene specimens, likely due to the impact-induced melting behavior visible in the high-speed images. In conclusion, ultra-high molecular weight polyethylene exhibits a brittle-like response, while high-density polyethylene exhibits apparent bulk melting. While the backface debris cloud velocities are similar for the two materials, ultra-high molecular weight polyethylene exhibits approximately 17% more mass loss on average than high-density polyethylene. Also, the perforation radii are larger in high-density polyethylene than ultra-high molecular weight polyethylene. This work serves as a foundation for comparing these two polyethylene materials. Currently, cutting-edge diagnostic equipment is being developed and implemented within the Texas A&M University Hypervelocity Impact Lab that will enable additional in-situ material characterization. These capabilities include a 450 kilovolt flash X-ray system, particle tracking algorithms, and digital inline holography. Detailed material characterization such as scanning electron microscopy, dynamic mechanical analysis, and differential scanning calorimetry are necessary to better understand the microstructure and chemistries of the polymeric materials and how the molecular structure affects the energy dissipation during hypervelocity impact events. Broadening the scope of the experimentation to include additional thicknesses of both materials and different projectile sizes will offer insight into the role geometry plays in the hypervelocity impact response of these polyethylene materials. Finally, it is necessary that thorough experimental results are coupled with the development and validation of high-fidelity computational models capable of predicting such hypervelocity impact phenomena. These slides provide the references given throughout the presentation.